Hi everyone, in today's video we're going to start our statistics and probability packet, and we'll call this skill 55. So the first thing you have to do is go over to the pink basket by my door and grab a copy of the packet that we're going to be using for this. We're going to be using this for the next 5 skills. These videos are going to work a little differently. Instead of having a mastery check at the end of each, we're just going to use the video as the grade for each of these skills. So it's very important that you follow through these packets and not lose them between each skill, because we're going to use them for 55, 56, 57, 58, and 59. All right, so now that you have that packet, if you don't, go pause the video and go get it. Now that you have that packet, first thing I want you to do is flip to the back page, and I want you to copy down the information that's on the screen here. These are some facts about probability and independence that we need to know for using this packet. This is not stuff that's given to you on the Regents, so we better know it and better understand it because we're not going to be given it as a formula sheet or anything like that. So pause the video, take a second, copy this down on the back of your packet. Okay, you've paused the video, you've copied it. Let's go through some of these questions here. So we're going to start with question number 1 in the packet. All of these skills are going to practice the same thing, which is probability, specifically with independence and with the term give it. So we'll go through what those terms mean in a second. But now question number 1 says a random sample of 152 students was surveyed on a particular day about how they got to school. The survey results are summarized in the table below. So whenever you get a table like this, it's usually a good idea to make a column for totals and make a row for totals. So it's not letting me write here. Let's see if I can get it to write on this screen instead. All right, it's not letting me write here either. All right, after a brief pause, I think I figured out how to write. So, like I said, let's make a row and a column for totals. So the car row adds up to 30. The bus row adds up to 100. And the walk row adds up to 22. And then our columns, let's add those up as well. So 20 plus 6 plus 4 is 30. And 24 plus 18 plus 80. These two add up to 42. So this adds up to 102. So a good check when you're doing these is that when you add all the columns up, they should equal the same numbers when you add up all the rows. So when I add these up, I get 132. When I add these up, I get 152. What did I do wrong? Oh, because 24 plus 18 is 42. This would be 122. Whoops. So anyway, the rows and the columns being totals is going to be super helpful when we go to actually answer the question. All right, so which statement is supported by the data? Choice A, the probability of being late given that a student walked is greater than the probability of a student walking given that the student was late. So whenever you hear the term given, that means that we're going to pretend like that thing is true. So in choice A, that they're saying the probability of being late given that a student walked, we're going to pretend like that's true. So where is that row or column where that's true? The walking column and row is right here. So if that's true, how many people does that apply to? Now there's only 22 total people in this survey, not 152, only 22 people, right? Because it says given that they walked. So that is a fact. They walked. We're only talking to these 22 people now. And what's the probability that they're late? Well, out of those 4 people or 22 people, 4 of them were late. So the probability of being late given that a student walked is 4 out of 22. And that's because there were 22 walkers and 4 of them were late. And it says that it's greater than, so we're going to go like that. And now we're going to do this part of the question, which is the probability that a student walked given that a student was late. Given that the student was late. So now we're going to given this column. And how many people are in that column? There were 30 people in that column. And now that we are only talking to the late people, how many of them walked? 4 out of 30. Well, this question wanted to know, is this true? Is this greater than this? 4 20-seconds is greater than 4 30ths. That is true. The answer to this is choice A. 4 20-seconds. If I split something into 22 and give you 4 piles, that's going to be bigger piles, or that's going to be more than if I split something into 30 piles and only give you 4 piles. Right? So the answer to this one is choice 1. Let's do the next question here. Number 2. The set of data in the table below shows the results of a survey on the number of messages that people of different ages text on their cell phones each month. If a person from this survey is selected at random, what is the probability that the person texts over 50 messages per month, given that the person is between the ages of 23 and 60? As soon as you hear the words given, stop looking at the whole table and only look at the row or column they're talking about. So where are the people between 23 and 60? That's this row right here. So ignore the rest of the table and only focus on this row of the table. And now that we figured out which row to look in, what's the probability that the person texts over 50 messages a month? That's that box right there. That blue circle is people that are over 50 and that only text over 50 messages, and their age is between 23 and 60. Which answer choice shows 157 is the numerator? Well, they all do. Which denominator shows all these numbers added up? 25 plus 47 plus 157. Those all add up to 229. So the answer to this question is A. All right, next question, number 3. A fast food restaurant analyzes data to better serve its customers. After its analysis, it discovers that the events D, that a customer uses the drive-thru, and F, that a customer orders French fries, are independent. The following data are given in a report. Given this information, P, F/D is. So let's talk about first what independence mean. If you're talking about probability and 2 events are independent, that means they have no impact on each other. So like if I were to say the probability of it snowing and the probability of pizza being served in the cafeteria, those 2 events are independent. They don't look out the window and decide, oh, it's snowing, we should serve pizza. Those 2 events are completely independent of each other. Mother Nature doesn't make it snow because they know we have pizza on the menu today, right? So in this case, they're saying that who goes through the drive-thru D has nothing to do with how many people order French fries. That means that people that are in the drive-thru don't order French fries more or less than people walking in the door, or people using DoorDash, or people doing a mobile order or anything like that. So now let's break down what all this means. P parenthesis F equals 0.8. That means the probability of any single person walking into this restaurant coming to this restaurant and ordering French fries is 0.8. And as a percent, that's 80%. So most people order French fries. And then the second row has a new symbol here, P, F, D. That symbol means and. That symbol means both of those things are true. So the probability of F and D, which means the probability of someone ordering French fries and going to the drive-thru, is 0.456. So that means 45% of people that are in the drive-thru order French fries. That's not true. That means that out of everyone that comes to this restaurant, 45% of them are French fry orderers that are in the drive-thru. That's a better way of saying that. So now we need to actually answer this question. Given this information, PF line D, that line means given. And that means, remember we said, given means we're pretending that that thing is true. So PF line D means given that probability of someone ordering French fries, given the fact that they definitely 100% went through the drive-thru. And the answer is which of these four choices? Now, I'm looking down at my notes here, if two events are independent, let's word it like this. PF line D equals PF. If two events are independent, then this is true. The probability of French fries, given that they went to the drive-thru, is just equal to the probability of French fries. Basically what it's saying is whether or not they went to the drive-thru doesn't matter. If these two events are truly independent, whether or not they went to the drive-thru is independent doesn't matter. And that's what they told us. They told us these two things are independent. So the probability of someone ordering French fries in the drive-thru is the same as just someone ordering French fries. And we already have that information here. The answer to this question is 80%. The fact that they were in the drive-thru did not impact how many of them ordered French fries. We already talked about that a little bit. Next question. Consider the probability statements regarding A and B below. We don't know what these two events are, but we know they're called A and B. The probability of A or B happening is about 30%, 0.3. The probability of both of them happening is 0.2, 20%. The probability of A given B is 80%, 0.8. So in that bottom row, that means B definitely happened. When that's the case, how many times does A also happen? So we have another probability thing here to talk about, and I'll write it out here. The probability fact we're going to deal with here is P A given B, probability of A given B is equal to the probability of both things happening over just the probability of B happening. So this fact says that the probability of A given B is equal to the probability of both things happening divided by the probability of just probability of B happening. And this is what we're looking for. We're looking for the probability of B happening, right? And we know two pieces of data here. We know that the answer to this is 0.8. They told us that in the original question. P, A, and B, we know that. That's right here in the question. And then P of B is what we're looking for. So we don't know that answer. So we need to solve this for X. I'm not going to show you how to solve for X because we should know how to do that. The answer to this question is 0.25. That means when you do 0.2 divided by 0.25, you get 0.8. All right, next question. Sam's team has a baseball game tomorrow. He pitches 50% of the games. There is a 40% chance of rain during the game tomorrow. If the probability that it rains, given that Sean pitches as 40%, it can be concluded that these two events are. Notice how the probability of it raining didn't change, right? There is a 40% chance of rain tomorrow. A probability that it rains given that Sean pitches is 40%. Sean pitched and that probability of rain didn't change. That means that him pitching had nothing to do with the rain. And that should make sense, right? Like you don't send a certain pitcher out based on whether or not it's raining. And I don't think that's true. So in any case, the answer to this one is these two things are independent. Number 5 is independent A. Next question. Which situation best describes conditional probability? Conditional probability means we're trying to see the probability of something happening, knowing for a fact that something else already happened. Like one condition is already true. What about the other condition? So which choice says that? Choice D says that. Finding the probability of an event occurring given, remember the word given has been the magic word for this lesson, given another event has already occurred. So this question, number 6, is D. Number 7, on a given school day, the probability that Nick oversleeps is 48%. And the probability he has a pop quiz is 25%. They probably don't need to say this sentence, but these two events are independent, meaning one of those things does not impact the other. His teacher doesn't see that he's absent and give a pop quiz, right? These two things have nothing to do with each other. It says they're independent. What is the probability that Nick oversleeps and has a pop quiz on the same day? So when two events are independent, all you have to do to find the probability of both of them happening, remember that upside down U means and, to find the probability of two things that are independent both happening, you just multiply the probabilities. This right here is a fact that we wrote down on the back of our packet. If I want to know the probability of both things happening, I just multiply the probability of each thing happening as long as they're independent. So Nick's oversleeping is 48% or 0.48. Nick's pop quiz probability is 25% or 0.25. Just multiply those, and that's the probability of both things happening. That works out to be 0.12. That means there's a 12% chance that Nick will sleep in by mistake and he'll have a pop quiz. I mean, he only has a pop quiz 1 out of every 4 days. And he only sleeps in half the days. So the chances of them both lining up is only about 1 in every 8 days. All right, number 8 is the next question. We have 2 more to go here in this section, then we'll stop for the day. The number of employees who work nights and weekends at a department store is summarized from the table below. They want N to be working nights and they want W to be working weekends. And they want to know, are nights and weekends independent events? And I'm going to tell you the answer is choice 1. Instead of going through all 4 choices, I'm going to explain why it's choice 1. So this right here is exactly the definition of two events being independent. Like we said in the last question, if two things are truly independent, then the probability of each of them happening separately when they multiply should equal the probability of both things happening. So let's look in the table at this. The probability of this in this table of someone working nights, how many people work nights? That's this column. 20 people work nights, right? 8 plus 12. Both people, the 8 and the 12 people, both of them work nights. So 20 people out of, if I add up all these numbers, that works out to 120. So 20 out of 120 people work nights. And now let's find the probability of people working weekends. That's this row. That's 48 out of the 120 people. So the choice A says, hey, if I multiply these, what do I get? Well, I get, using simplifying math, let's see, it works out to, well, it works out to 8 out of 120. What does that reduce to? That works out to 1 out of 15. So the probability of each of these being multiplied works out to, let's do a third color. Both of those things multiply, work out to a 1 in 15 chance. Now, if these are truly independent, then both of these things happening at the same time should have the same probability. So what is the probability someone works nights and weekends? That's right here. Those 8 people work nights and work weekends. That's 8 out of 120 people. And I just said that same exact number. That simplifies to 1 out of 15. So because those two numbers are the same, these two events are independent. And that's because when you multiply two things separately, if you get the same result as both of them definitely happening, then that means that the two events are independent. All right, and last question for the day. Whoops, forgot to erase. Last question for the day. Oh, we're skipping question 9 because it's just a repeat of the next question from earlier. Now we're going to move on to the last question. You can cross off question 9, and then let's work on question 10 as the last question. It says, suppose events A and B are independent, and the probability of both things happening, A and B, is 0.2. Which statement could be true? Once again, I'm going to tell you the answer is B, and then I'm going to tell you why the answer is B. Remember, if these two things are both happening, then that means that both things separately happening, then multiplied, should be the same answer, right? So the answer to this right here is 0.2. You'd figure that up here. And they said, hey, what other numbers could make this statement true? Well, if I put 0.8 here for P of A and 0.25 for this one, if I multiply 0.8 times 0.25, guess what? I get 0.2. All the other numbers here do not multiply to 0.2. These add to 0.0, these add to 0.2, but that's not what we want. We wanted to know, do you know the fact that multiplying two events separately should get the same answer as the probability of both of them definitely happening? So that's it for packet. The packet first and second and third page, skill 55 is all we did today. That was questions 1 through 10. That's all for today. Don't lose this packet. The next video is going to go through skill 56. So that's all. Thanks for watching.